Hey all, so in this video we're going to look at functions and just sort of an introductory version. We'll have another couple sections coming up where we extend this material. For this first one, some basic definitions. First one is a relation, is a set of ordered pairs. So just like looking down here at this first example, these would all be examples of relations. We have an input and an output. There's no other conditions on that other than there's just a set of ordered pairs. Whether or not a relation is a function, that's where we start getting some conditions, and this is sort of the more important part. A function is a rule that associates each input with exactly one output, or if you want to think of it in terms of x's and y's that are a little more familiar, for each x there can only be one y. Domain is going to be the set of our input values, so what we would think of as the x's, and that's going to be our independent variable is another name for that. And the range is going to be a set of the output values, or the dependent variable. We choose a value for x, and then y depends on that value of x, so independent and dependent. So domain is associated with x's, and range is associated with y's, or inputs and outputs. Let's see how that looks with some examples. So determine if a relation is a function. Identify domain, range, ordered pair from an ordered pair table or graph. So these is just going to be a few different views of is it a function, and then identifying domain and range. So for this first question, we're asked to select all the following tables that represent y as a function of x. So what that means is, again, for each x there can only be one y value associated with that. So if I look at this first table, oh no, don't know why that's there. There we go. If we look at this first table, when x is 4, or when the input is 4, the output is 5, input's 8, output is 10, input is 15, output is still 10, you might think, wait, there's duplicate 10s, is that an issue? No. And the reason is when x is 8, the only thing y can be is 10. So for this input, there is exactly one output. When x is 15, the only thing y can be is 10 again. So you can have repeated values of y, but for a given x, there can only be one output associated. So for this, we would say, yes, that one is a function. 4, 5, 8, 10, 15, 12. So again, for each of these values of x, there's only one output, so that one is a function. But you get down to here, when the input, when x is 8, the output could be 10 or 12, so that has two different values associated with that input, so that one is, not a function. So that was from a table. This next version is going to be from a graph. There's something called the vertical line test, and it reads, if any vertical line drawn would intersect the curve more than once, the graph does not represent a function. So that seems fairly straightforward. Basically, if I draw a vertical line, we'll do it over here, and I hit the graph more than once, and you can see that I do on this one, then it's not a function. And the reason for that is, again, if x is 1, the output could be 1 or 2, so this would be not a function. Here, anywhere I draw a vertical line, I only hit the graph once, so that's a yes, that is. Here, if I draw a vertical line, I can hit it 3 different times, so no, that's not a function. And this one would be yes, because, again, it passes vertical line test. For this question, which quantity represents the independent variable? And this is just to get you used to the terminology. So remember, the independent variable is what we would associate with x, or the x-axis. It's the input down here. So in this case, the quantity, what is it, time? So time would be the quantity associated with the independent variable, and then which quantity represents the dependent variable, that would be the vertical axis, which is distance in this case. I dropped the pen. Next we have state the domain and range of the relations below and determine if it's a function. Okay, So remember, domain is associated with the x values or the input or the independent variable, all the same in this case, and then the range is associated with the output, the y values. And there's this little f of x that's showing up. We're actually going to get to that down here on this next table, but it's going to be our function notation that we're going to see in just a second. So the independent variables, and the way that in the computer, I think there's an answer box and it has the brackets around the box, so you don't have to type these brackets. But for the domain, we would have what's called bracers. It's kind of the squiggly brackets, and that's how we do a list. Again, I don't think you have to type it on the computer. I think there's just an answer box with the bracers around the box. But this would be -7, 11, 31, 32, 34, 44. Those are supposed to be 4s, so it's really bad looking 4s. Let's see. And then the range on this one would be the outputs, so that's our same notation. And I think on the boxes on homework, I believe the directions said that the order that you write them in doesn't matter. Traditionally, we would put these in from small to large, but I think for typing in the boxes, it's cool to just take them straight off the list like that. And then determine if it's a function. So the easy way to do that is to look for repeated x values, and we don't have any repeated x values, so that means each of these has just one output associated, so we would say, yes, that is a function. For this one, determine if it's a function, and same thing, domain and range. So the domain for this is going to be 7, 6, 5, 4. And the range in this case is always -7. So we just do that for a range. And again, we can have repeats in y because when x is 7, the output is only -7. When x is 6, the output is only -7. If you graph that, you would get a horizontal line that would totally pass the vertical line test. So this one is also a function. For number 5 here, the function f of x is defined by this graph. Using the graph, identify the domain and range. Okay, so what I might do first, I'm just going to list these points here, and then I'll write it out. And this one would be a function because it passes the vertical line test. We don't have points stacked on top of each other. So that one looks to be at -4, 3. This one looks to be at -1, 5. And that one is 2, -1. So for the domain, that's our x's. So -4, -1, and 2. Oops, check that. And for a range, it's going to be 3, 5, -1. And that would be that one. Next, we get a little bit more notation. So this is the function notation, the f of x that we're seeing up in those earlier ones. So the notation y equals f of x defines a function named f. It's read y is a function of x, or y equals f of x would be another way of saying that. The x in this f of x is the input value or the independent variable, like we we're just seeing. F is a symbol that denotes the function rule. So if I had something like f of x equals x squared plus 3, the function rule in this case would be that we have an input, we square it, and then we add 3 to it. So we take our input, square it, add 3 to it. That's what the f is representing. That's the rule that we're applying to that input. And then letter y, or f of x, this side represents the output or the dependent variable. So x is our input, f of x is our output. When we have, and we'll see a bunch of examples with this, if we're evaluating a function at a value like f of a, where a could be a number or an expression, it means to evaluate the function at x equals a. So for instance, if this said f of 7, that means we would be plugging 7 in for that x right there. So that the x is being replaced by 7, probably should have written 7 right there, but that means we're plugging in for x. If we have f of x equals a value, then that means you're solving, that means you know the y side, and you're solving for an x. So for instance, for this, if I had f of x equaled 7, that would mean I would be solving 7 equals x squared plus 3. So f of 7, I really probably should have written, let me get rid of that. I probably should have written that right there. So f of 7 equals 7 squared plus 7. This is replacing x, and so it's going in for x. If I have f of x equals 7, that means y equals 7, and I would be solving for x. So let's see what that looks like down here. So given the function g of x, and then it doesn't have to be f, it can be any letter that's denoting the function. F and g are kind of the two most common generally. So the function g of x is given, so there's our inputs and our outputs. Evaluate g of 5. So the 5 is replacing x, so that means we're looking for when x is 5, what's the output, and that would be 1 right there. So when the input is 5, the output is 1. Solve g of x equals 2. This is like saying when y equals 2, what does x equal? And so when y equals 2, it looks like the x is 4. So for this version, we know x, we're looking for y. For this version, we know y, and we're looking for x. Same thing here, but with a graph. So evaluate f of 4. So we come over here and we look where the input is 4, the output in that case is 2. So when x is 4, the output is 2. Here this is asking us to solve when y equals 4, what x would make that happen. And so where is y 4? Y is 4 right there. And it looks like that happens at x equals -1. Oops. For this next bit, we have an actual equation that we're going to plug into. And so here we have evaluate this function at 4. So if I'm finding f of 4, that means I'm going to plug in 4 for the x, and -2 times 4 is -8 minus 7. So when the input is 4, the output is -15. For this one, it's saying f of x equals -3, so that means I know the output on this one and I'm solving for x. So notice, and the directions are also kind of a tip as to what's going on. If it's evaluate, that means you're plugging in for x, you're evaluating this function at x. If it's solve, that means you know the output and you're solving for what value of x would make that true. So here we have f of x equals -3, and we're going to plug that in and then solve for x. So here we would add 7 to both sides. And -3 plus 7 is going to be 4 equals -2x. And then dividing the -2 over, we would get x equals -2. Oops, let's see, I need that there so I can see the function. When we're evaluating, it doesn't have to be at a number. It can be at basically anything that you put in these parentheses. That's what's going to replace the x. So here, if I'm finding f of a over 9, that means I'm going to put a over 9 in anywhere there used to be an x. So this is going to be negative 2 times a over 9. My a's and 9's kind of look the same. And then minus 7. Cleaning that up slightly, I could write that as a couple of ways. I could write it as negative 2/9 a minus 7, or I could have the a in the numerator, negative 2a over 9. Those mean the exact same thing. But there's that function evaluated at a over 9. For this one, we're going to have a minus h. That's what's replacing x. So I'll just write that there. So we'd have negative 2 and then a minus h minus 7. And for here, we'll just go ahead and distribute that negative 2 through. So negative 2a minus and minus make that a plus 2h and minus 7. Same idea, we'll have to do a little bit more math on this one. So given the function f of x equals negative 7 plus x squared, calculate the following. So we're going to evaluate this function at x plus 1. So that means we're going to put x plus 1 in for that x. And if you remember how to do the shortcut on these, where the perfect trinomial squares, where you go x times x makes x squared, x times 1 is x, and then you double it for 2x, and 1 times 1 squared would make 1. That's great. We're going to review that in chapter 3. For right now, I'm just going to show it as a FOIL, and we'll review that other expansion when we review factoring later in the course. So here, x times x is going to be x squared. On the outside, I get plus x. On the inside, I get plus x. And at the end, I get 1. So negative 7 plus x squared. Actually, let me combine my like terms in one step since I'm going to run out of room anyhow. I have a negative 7 and a 1 right there. And I have a couple of x's right there that I can combine. So let me do that all in one row here. X squared and plus x. Remember, there's invisible 1's out front. So 1x plus 1x would give me 2 x's. And then minus 7 plus 1 would give me negative 6. For this one, it's saying take the original function, which is f of x, and then add to that the function evaluated at negative 5. So f of x would be right here. That's just our original function. And then I'm supposed to add to that f of negative 5. So negative 7 plus negative 5 squared. So negative 7 plus x squared. This is going to be negative 7. Negative 5 times negative 5 is going to be plus 25, because there's a double negative right there. And then I'll just go ahead and combine that first, and then I'll add the 7 to it in a second. So negative 7 plus 25 would be 18. So that's our f of negative 5 piece. And now we're just going to add that to this negative 7. No reason you couldn't do that all in the same line. If this had been a minus, these parentheses become a lot more important. If you didn't combine it all down to one thing, you'd have to be careful to get that distributed. To me, I prefer to kind of get everything grouped up and then add or subtract all at once. So negative 7 plus 18, so that's going to be 11. So let's go x squared plus 11. And that's it for this section. We'll see some more function notation in the next section.